Hi, my name is Dr.AhMath. Welcome to the course of Biophysics 1. In this video, we're going to discuss the solutions for the quiz problems on a continued equation. So the continued equation basically is the conservation law of mass. It basically tells us that, hey, amount of the fluid which is passing through the cross-section area per unit of time is the constant, is unchanged. So the amount of the fluid, we call this as the volumetric flow rate, which is the multiplication of the area to the velocity, is going to be the same in any part of the pipe. So the multiplication of this area to this velocity is going to be the same. So we are going to solve a couple of problems. The first problem is water flowing through a garden hose of diameter 2.74 centimeters fills a 25-liter bucket in 2.5 minutes. So find the volumetric flow rate. So basically the volumetric flow rate, or we denote it as the IV, is equal to the area times the velocity. So the area, so the units of the area is meters in the square, and the units of the velocity is meters per second, right? So the units of the volumetric flow rate is meter in the cube over second. So what I have to do is I just need to use the units of these two things. So 1 liter is equal to the 10 in the power of minus 3 meter cube. So it means that 25 liters is going to be equal to the 25 times 10 in the power of minus 3 meter in the cube. So what I have to do is I need to write down the units in a way in order to get the meter cube over the second, right? So I need to write as 25 liters, or 25 times 10 in the power of minus 3 meters in the cube divided to the time. So in this case, the time is 2.5 minutes. It's 150 seconds, right? 150 seconds. So what I have to do is I just need to divide 25 to the 150. If I divide 25 to the 150, it's going to be 0.6016, 167 times 10 in the power of minus 3 meter cube over second. So this is the volumetric flow rate. Yeah. So this is the volumetric flow rate for this problem. So next one is the water flowing through a garden hose that was a diameter 2.6 centimeter fills 20-liter bucket in 2 minutes. What's the speed of the water living at the end of the hose? So in order to do this, we need to again use the same equation. So the IV is equal to the area times the velocity. So we can find the volumetric flow rate just using the information that water fills the 20-liter bucket in 2 minutes. It gives us the measurement for the volumetric flow rate. So we can find area by knowing the diameter of the hose, and then we can find the velocity from this equation. So let's find first of all the volumetric flow rate. It's going to be equal to the 20 liters, which is 20 times 10 in the power of minus 3 meters in the cube, divided to the 2 minutes, which is 120 seconds, right? So let me divide this to the 20 over 120. It's going to be equal to the 0.167. Again, so the times 10 in the power of minus 3 meter cube over second. So in order to find the area, you need to imagine again, so you've got the garden hose, where if you just cut this somewhere of this hose, you are going to get a circle. So this circle, and the area of the circle, so this is the area, right, of the cross section. So if you would have the rectangular hose, then the area is going to be a rectangle, right? So the area of the cross section. So in this case, the area of the cross section is the area of the circle, and the area of the circle is found using this formula. So the pi times the diameter of the circle in the square. So we are going to multiply the pi to the radius in the square. So if the diameter is equal to the 2.6 centimeters, then the radius is going to be equal to the 1.3 centimeters. So we have to write this 1.3 centimeters, but we have to always write these things in a meter. So times 10 in the power of minus 2 meters, and this thing in the square. So what I have to do is I need to square 1.3. It's going to be equal to the 1.7 or 1.69. 1.69 times pi times 10 in the power of minus 4, right? Because 10 in the power of minus 2 in the square, it's going to be 10 in the power of minus 4 meters squared. So we have to just make the multiplication. We have to multiply this to the pi. It's going to be 5.31. So 5.31 times 10 in the power of minus 4 meters in the square. So now what I have to do is I need to find from this equation the velocity, right? In order to do this, this area should go to the left. So the velocity is going to be equal to the volumetric flow rate over the area. So I'm going to put the volumetric flow rate, it's going to be 0.167 times 10 in the power of minus 3 meter cube over second, divided to 5.31 times 10 in the power of minus 4 times meter in the square. So we can cancel out this meter square with this cube, and we'll have meter over second, which is the proper unit of the velocity, right? So now we need to do the calculations. So 0.167 over 5.31, it's going to be and times 10, right? So this 10 in the power of minus 4, if it goes up to the numerator, it becomes plus 4. So, and then we can add this with the power of this 10 on the numerator. It's going to be minus 3 plus 4. It's going to be plus 1. So if I divide this number to this one, I'm going to get 0.0315 times 10 in the power of minus 3 plus 4 times meter over second. So the answer is going to be equal. So this is going to be simply 10. I can just multiply this. It's going to be 0.315 meters per second. Nice. So this is the velocity of the water. So let's go to the next problem. So problem number 3, water flowing through a garden hose with a diameter 2.6 centimeters fills a 20-liter bucket in 2 minutes. Okay, so which is very similar to our previous problem, right? So previously we know that the volumetric flow rate is going to be equal to the 0.167 meter cube over second. And we also know the velocity of the fluid from the previous problem. It was equal to the 0.315 meters per second, right? So a nozzle is now attached to the end of the hose. And if the nozzle's diameter is 1/3 of the diameter of the hose, what is the velocity of the water leaving from the nozzle? So basically, we're dealing with the problem where one diameter, it's now connected with the nozzle like this. So its diameter is going to be 1/3 of the diameter of the hose. So what we have to do is we need to know what is going to be the speed of the water, right? Which is going out from here. So V2, what is this? So in order to find this, we can use the continued equation basically. And so actually I don't need to use the continued equation. The continued equation gives us the intuition. So the area times the velocity 1 is equal to the area 2 times the velocity 2, right? Let's find the velocity from here. So the first thing which I have to do is I need to divide the volumetric flow rate, so area times the velocity, right? So the volumetric flow rate over the area of the second one. So in order to find the area of the second one, if you remember, the diameter is equal to 2.6 centimeters, right? So it means that the radius is so the diameter here is going to be 2.6 times 3. So this is going to be the diameter of the circle, right? But I need just the radius. So in order to find the radius, I have to divide this to the 2 again. So it's going to be 2.6 over 6. 2.6 over 6, it's going to be 0.43. So this is the radius of the nozzle. So we need to find this area to, it's going to be pi times radius in the square. It's going to be equal to the pi times 0.43 times 10 in the power of minus 2 meters. So it's going to be 0.43 in the square times pi. So 0.59. So 0.59 times 10 in the power of minus 4. So I have to plug this to here. It's going to be the volumetric flow rate was equal to the 0.167 times, sorry, so volumetric times 10 in the power of minus 3 again. So here we have 10 in the power of minus 3 meters per second. So times 10 in the power of minus 3 meters cubed per second divided to the second velocity, 0.5910 in the power of minus 4 meters in the square, right? So it's going to be equal to the 0.167 over 0.59. It's going to be equal to the 0.28. So 0.28 times 10, it's going to be 2.8 actually. 2.8 meters per second. So the second velocity is going to be equal to the 2.8. So while the V1 was equal to 0.31, right? So V1 is equal to 0.31. So it gives us actually the intuition how the velocity is changing again, right? So if the diameter of this pipe or of the pipe is changing, is decreasing 3 times, then the velocity should obviously increase, right? But we can see that the velocity is not increasing 3 times, because if you multiply 0.315 to the 3, you will get roughly 1, right? Or 0.9 or something like this. So obviously it's increasing more than 3 times, right? So if I just divide V2 to the V1 in order to understand how many times the velocity is increasing, so 2.831 over 0.315. It's going to be roughly 9 times. It's going to be equal to the 9. Okay, so which is understandable, right? Because in this formula of the volumetric flow rate, I is equal to area times the velocity, right? If you change the cross-section area, for example, if you increase the cross-section area to the 2 times, then the velocity is going to be decreased 2 times. But if you change the radius, it's going to be different, because for the cross-section area, you will have the radius in the square here times the velocity. It means that if you decrease the radius 3 times, so basically if you just plug here 1 over 3 to here, right? So in the square it becomes 1 over 9, right? So it means that you are decreasing the cross-section area 9 times when you are decreasing the radius 3 times. So that is why the velocity is increased 9 times. Okay, so you need to understand what happens when you change the cross-section area and what happens when you change the radius of the pipe. Let's go to the next problem. What is the average flow speed of blood in aorta if its diameter is equal to the 2.4 centimeters and volumetric flow rate is equal to the 0.1 liters per second? And again, we need to use the equation that volumetric flow rate is equal to the area times the velocity, and from here we can find the velocity is going to be the volumetric flow rate divided to the area. So so I've got here the aorta with its diameter is equal to the 2.4 centimeters. So the area of this aorta is equal to the radius, which is the half of the diameter, 1.2 centimeters, which is 1.2 times 10 in the power of minus 2 meters in the square times pi. So we have to just plug this to this equation. So 0.1 liters means 10 in the power of minus 3 meter cube over second, divided to 1.2 in the square. It's going to be 1.44 times 10 in the power of minus 4 meters in the square. So I'm going to divide this. It's going to be 0.1 time divided to the 1.44. It's going to be 0.069 or 7 roughly times 10 meters per second, or this is going to be equal to the 0.7 meters per second. So this is the average speed, right? Good. Volumetric flow rate over the area. Let's go to the next problem. What is the total cross-section of the arteries if there are 160 of them and their average diameter is equal to the 0.4 centimeters? So you've got basically one arteria, second one, and so on, and 160. So we assume that all of them are going to have the same diameter. And what is the total cross-section? So it means that I need to find the cross-section of the first one, the second one, the third one, and the 160th one, and then I have to add all of them. So again, the diameter of each of them is equal to the 0.4 centimeters, right? It means that the radius is going to be equal to the 0.2 centimeters. So it means that 0.2 times 10 to the power of minus 2 meters. So the area of each one artery is equal to the pi times radius in the square. It's going to be 3.14 times 0.2 times 10 to the power of minus 2 meters in the square. So let me multiply this. 0.2 times 0.2, it's going to be 0.04. So this is times 3.14. It's going to be 0.1257. So 0.1257 times meter in the square. So this is the area, cross-section area of one arteria. So if you have 160 of them, you have to just add this number 160 times. It means that it is equivalent to just multiply this area to the 160. So it's going to be equal to the 0.1257 meters in the square times 160. It's going to be equal to the 20.1 meters in the square. So roughly total cross-section area of all the arteries is equal to the 20 meters in the square. So let's go to the problem number 6. If the cross-section, total cross-section area of arteries is equal to the 20 centimeters in the square, yeah, so the only thing which bothers me, because we forgot about here, 10 in the power of minus 4, sorry. So meters in the square, right? So 20 times 10 in the power of minus 4 meters in the square, which is equivalent 20 times to the centimeters in the square. Okay, so these two things are equivalent. So when you square, so 20 centimeters is 20 times 10 in the power of minus 2, basically. 20 centimeters is 20 times 10 in the power of minus 2 meters. But 20 centimeter in the square, it's going to be 20 times 10 in the power of minus 4 meter in the square, right? So it's going to be minus 4, not minus 2. So that is why 20 times 10 in the power of minus 4 meters is going to be 20 centimeters in the square. Okay, so if the total cross-section area of the arteries is equal to the 20 centimeters square, and the average flow rate is equal to the 5 centimeters per second, what is the volumetric flow rate of the blood? Okay, so basically the volumetric flow rate of the blood is equal to the area times the velocity, right? So we are given that the total cross-section area of all the arteries is equal to the 20 centimeters, right? So 20 times 10 in the power, or we can do this. Let's do this with the meters. So 20 centimeters in the square is 20 times 10 in the power of minus 4 meters in the square times. So speed is 5 centimeters per second. It's going to be 5 times 10 in the power of minus 2 times meter per second, right? So it's going to be equal to 20 times 5 is equal to 100 times 10 in the power of minus 4 times minus 2, it's going to be plus minus 6 times meter and the cube over second, right? So 100 is multiplied to the 10 in the power of minus 6. It's going to be 10 in the power of minus 4 meter cube over second, right? And I can write this as 0.1 times 10 in the power of minus 3 times meter cube times 1 over second. And if you remember, 10 in the power of minus 3 meter cube is 1 liter. So it's going to be 0.1 liter per second. Nice. So the problem number 7, so how does the flow speed of the ideal fluid change if the cross-section of the tube is doubled? Okay, so I need to write down the volumetric flow rate. So the A times the V. So the multiplication is the same. If you change the cross section, then the velocity is going to be also changed. So because the multiplication should be always the same. So what I have to do is I need to substitute this A with something new. For example, in this case, the new thing is going to be, so the cross section is doubled, right? So the cross section is going to be increased. So it's going to be 2 times A. So I'm going to substitute this 2 times A. So what I have to 2 times A, what I have to write here in order to get the same volumetric flow rate. So I need to write this as 1 over 2 velocity, right? So in this case, I will get again IV because this 2 is going to be compensated with 1 over 2. Okay, so it means that if the tube, the cross section of the tube is increased twice, right, is doubled, then the speed of the fluid is going to be decreased